right? So I welcome you all for today's EMF session. A very good morning to you all. Let me recollect the things which I have discussed in my last class. I have done some related problems. Before to that, I have discussed about the reflection of plane wave normal instance. So do remember one thing, that reflection of plane wave normal instance, reflection of plane wave oblique instance. Right. Right. So reflection of plane wave normal instance, reflection of plane wave oblique instance. Among these two, one question compulsory. So reflection of plane wave normal instance in the sense what? When plane wave instance normally, when plane wave instance normally on a boundary, it is called as a normal instance. And um, in normal instance, I have defined incident waves, reflected waves, and transmitted waves. Right. So when EM wave instance on a boundary, generally what happens? Part of the wave transmits and part of the wave reflects back. And it depends on the type of boundary, whether the boundary is between free space dielectric, or whether the boundary is between free space conductor, or whether the boundary is between dielectric. It depends on how much wave is transmitted and how much wave is reflected. That amount depends on the type of boundary, right? So instant waves, reflected waves, and the transmitted waves I have defined, and from that applying boundary conditions and simplifying and finding out reflection coefficient and transmission coefficient. So these are the final expressions. Reflection coefficient eta 2 minus eta 1 by eta 2 plus eta 1. Transmission coefficient 2 eta 2 by eta 1 plus eta 2. Right. So transmission coefficient and reflection coefficients will gives you how much wave is transmitted and how much wave is reflected back. Those things it will gives you. Right. And after determining reflection coefficient and transmission coefficient, as a case one, I have considered region 1 perfect dielectric and region 2 perfect conductor. So perfect conductor in the sense conductivity is infinite, right? So therefore determining eta 1 and eta 2, eta 2 will become 0, right? Because conductivity is infinite, right? So equating to 0, we will get um, transmission coefficient 0. That means whenever one region is conductor, you do remember this, whenever one region is conductor, uh, mm, uh, the entire wave reflects back, right? Whenever one region is conductor, the entire wave reflects back, because EM wave does not exist inside a conductor, right? It exists only on the surface of the conductor. It cannot penetrate through a conductor. So therefore, transmission coefficient is 0 and reflection coefficient is -1. That means the entire wave reflects back with the phase reversal. That is what I have shown in the figure, right? So this is about reflection of plane wave normal instance. And coming to the related problems, I have done some related problems here, based on the discussion which I had earlier, right? So, and this problem is related to normal incidence. When EM wave incidents normally, depending on that, we have done a problem, right? Um, First of all, whenever a problem is given like this, the very first step is you need to identify the boundary. What is region 1 and what is region 2? What are the characteristics of region 1 and what are the characteristics of region 2? Right? So note it down, and determine intrinsic impedance region 1 and intrinsic impedance region 2, and depending on that, and taking some relations, right? We can do the problem, and that I have done in my last class. If you have any doubts, go through the YouTube video which I have uploaded in the Edmodo app, right? So let us move on without wasting much time. Let us move on to another topic, reflection of um, plane wave, oblique instance. Reflection of plane wave, oblique instance, right? So reflection of plane wave, normal instance is over, and now reflection of plane wave, oblique instance, right? Um, so whenever, once again, I will repeat the same discussion. Um, Whenever a plane wave instance obliquely on a surface, on a surface on a surface, in general, part of the wave part of the wave reflects, and part of the wave part of the wave transmits, right? Part of the wave reflects and part of the wave transmits, right? And whenever oblique incidence is considered, we have to take, um, we have to take horizontal polarization and vertical polarization into consideration, right? So whenever oblique incidence is considered, we have to take horizontal polarization and vertical polarization into consideration, right? So we need to, before going ahead with this topic, we need to understand what is horizontal polarization and what is vertical polarization, right? So earlier, for normal instance, no need of considering horizontal polarization and vertical polarization, right? So because the direction of electric field is same in all the cases, right? So let me go back and explain here, right? So here, in this case, right? So here, the direction of electric field, if you observe here, right? So this is the direction of electric field, incident electric field, and transmitted electric field, and reflected electric field, right? Incident electric field, transmitted electric field, and reflected electric field. The direction is same, right? The direction is same, and the direction can be indicated, right? The direction can be indicated using a coordinate system. So here this is x, so therefore the direction of electric field component is in x direction, ax bar, right? Ax bar. But whereas whenever wave incidents obliquely, right, whenever wave incidents obliquely, um, um, we need to consider the direction of electric field in a more clearly, right? In a more clearly, right? So because as you know that polarization is defined in terms of electric field, and it is nothing but the orientation of electric field in space with respect to time, how electric field is oriented, how electric field is changing in space with respect to time, that is polarization, right? So therefore whenever wave incidents obliquely, automatically that wave makes some angle, right? Some angle with the plane of incidence, and some angle with the vertical line with respect to the plane of incidence, right? So we need to consider how the electric field is changing, right? So more clearly let me explain so that you can understand more clearly, right? um, let me draw the figures first so that it will becomes even more clear to you. Let us say this is the boundary, right? Boundary between what? Between region 1 and region 2, right? So region 1 and region 2, and let us say this is y-axis, and this is z-axis, right? So x-axis is perpendicular, right? Perpendicular to the screen, right? So like this you can look at this. This is mm, this is x-axis, right? So this is x-axis, right? And now um, wave instance, right? So this is the incoming wave. So incoming wave is traveling like this, and incidence on a boundary, right? So this is the incoming wave, right? So in other words, this is called as incident wave, right? Incident wave. So whenever wave incidence on a boundary, and this is called as angle of incidence, right? Angle of incidence, that is theta 1, angle of incidence. And generally part of the wave reflects, right? So this is the reflected wave, and part of the wave transmits. And one more thing, this angle is angle of reflection, right? Angle of reflection. This is the vertical line, z-axis, and part of the wave transmits, right? Part of the wave transmits. So this is transmitted wave, transmitted wave, and this is called as angle of refraction, right? Transmitted wave is nothing but refracted wave, right? So transmitted wave in the sense refracted wave, right? So wave refracts and depending on type of media, right? Refraction and reflected, right? So therefore theta 3 is angle of refraction, right? So theta 1 is angle of incidence, theta 2 is angle of reflection, and theta 3 is angle of refraction, right? And here one more thing is the angle of incidence and angle of reflection are the same, right? So EM wave when incidence on a boundary, it reflects with the same angle that of incident angle, right? Reflects the same angle with that of reflection incident angle. Right? Therefore, theta 1 and theta 2 are the same, right? Theta 1 and theta 2 are the same, right? But angle of reflection is different. Theta 3 is different, right? And um, right. So here like this, and let us also um, indicate the electric field and magnetic field components, right? Electric field and magnetic field component. So incident magnetic field and incident electric field, right? Incident magnetic field and incident electric field, right? So this is how we can indicate the electric field, right? So here electric field I have indicated with the dot, right? Electric field I have indicated with a dot, in the sense what the electric field is in positive x direction, right? So this is x, so therefore a dot in the sense what the electric field is perpendicular to yz, right? Perpendicular to the surface yz, right? So this is y, so therefore yz, it is perpendicular to yz, right? And this is the direction of magnetic field, and this is the direction of wave propagation ak bar, right? So wave is propagating in this direction, wave is propagating with a certain angle, right? With certain angle with respect to the vertical axis, that is z axis, right? So because as we know that ae bar, right? ae bar is the direction of electric field, ah bar is the direction of magnetic field, and ak bar is the direction of wave propagation, and they are mutually perpendicular, right? They are mutually perpendicular, right? So therefore here if this is the direction of wave propagation, um, and direction of electric field and direction of magnetic field, and similarly with respect to the reflected wave, right? With respect to the reflected wave, so this is the reflected electric field, and this is the reflected magnetic field, right? And this is the direction of wave propagation. Direction of wave propagation is this, right? So similarly, transmitted wave will transmit as it is, ei and h sorry, transmitted et and ht, and this is the direction of wave propagation, right? So this is how we can indicate, right? Indicate the direction of electric field, magnetic field, and wave propagation, right? Wave propagation. So these three are mutually perpendicular, right? Three are mutually perpendicular. So dot EI, electric field, is indicated with the dot in the sense perpendicular to the surface, right? In other words, the screen, right? So this screen, it is perpendicular, and this is the direction of magnetic field and direction of wave propagation. So therefore, those three are mutually perpendicular to each other, right? So this is how we can indicate it. And here, if you observe this, right? If you observe this, the direction of electric field, uh, uh, this is the boundary, plane of boundary, right? So this is plane of boundary, right? This is the plane of boundary, right? So this is the plane, right? Plane of boundary, plane of boundary, right? So plane of boundary is xy plane, right? Plane of boundary is xy plane. So to xy plane, the electric field, to xy plane, the electric field is horizontal, right? To xy plane, the electric field is horizontal, right? Electric field is horizontal. Now can you imagine yourself, the electric field is horizontal to xy plane, right? You just imagine it, right? The electric field is horizontal to xy plane, right? So here I have indicated the electric field as dot in the sense the electric field is coming outside the surface, right? So therefore, perpendicular to yz plane, right? Perpendicular to yz plane, right? So therefore, electric field, right, here, electric field is perpendicular to electric field is perpendicular to yz plane, and electric field is is horizontal to xy plane, right? Horizontal to xy plane, right? And this type of polarization is called as horizontal or perpendicular polarization, right? Horizontal or perpendicular polarization, right? So this is called as horizontal or perpendicular polarization, right? So horizontal or perpendicular polarization means what? Let me write down. When the electric field vector is horizontal to the boundary surface and perpendicular to the plane of incidence, plane of incidence, this is often termed as horizontal or perpendicular polarization, right? So this is termed as horizontal or perpendicular polarization, right? So electric field here I have summarized in these 2 points. Electric field is perpendicular to YZ plane, right? YZ plane is also called as plane of incidence, right? Plane of incidence. So this is plane of incidence, and this is uh, plane of boundary, right? So this is plane of boundary, right? So here, as shown, right, as shown in the figure, um, this is so we can explain the horizontal and um, perpendicular horizontal or perpendicular polarization, right? So this is one type of polarization. Now I will draw one more figure here, then you could understand very clearly the difference, right? So this is boundary, this is the vertical axis, right? So y, this is z axis, and this is as usual x axis, right? So now the wave is traveling like this, and incidence, right? The wave is traveling like this, so this is incident wave, incident wave, right? Incidence here, and this is angle of incidence theta 1, and reflects, right? Reflects back. This is called as reflected wave, angle of reflection, and a part of the wave transmits, and this is called transmitted wave, and this is angle of refraction, right? Angle of refraction, right? So now let us indicate the electric and magnetic fields. So this is the incident magnetic field, and this is the incidence electric field, right? And reflected magnetic field, reflected electric field, transmitted electric field, and transmitted magnetic field, right? So here, for the previous figure and this figure, there is a difference, right? There is a difference. You just compare, these two figures. You just compare the direction of electric field here, direction of electric field, and direction of magnetic field here, right? So here in first case, in case one, the electric field, right? Electric field here. So what is the electric field? Direction of electric field ax bar, and here the direction of electric field ax bar, and here the direction of electric field is ax bar, right? So here the direction of electric field, right? Direction of electric field is AX bar, right? Direction of electric field is AX bar. It is very clear, right? So dot in the sense it is coming outside, right? Coming outside the screen. So therefore, coming outside the screen in the sense what is it? It is nothing but x-axis, right? So AX bar. But whereas in case 2, in figure 2, what is the direction of electric field? Instant wave. This is the direction of electric field. Electric field is directing in this direction. And reflected wave. For reflected wave, this is the direction of electric field. And transmitted wave. This is the direction of electric field. Right? So therefore, different directions. Instant and transmitted wave, they are the same. But whereas reflected wave, the direction of electric field is different. Right? Direction of electric field is different. Right? So the electric field, and here magnetic field is in the same direction. So here magnetic field is indicated with a dot. Here is dot, and here is dot, and here is dot. Right? In 3 cases it is dot. That is instant wave dot, reflected wave dot, and transmitted wave dot. That means the direction of the direction of magnetic field, the direction of magnetic field is AX bar, right? Direction of magnetic field is AX bar here. And previously direction of electric field is AX bar, and here in the second figure direction of magnetic field is AX bar. But in fact the polarization is defined in terms of electric field, not in terms of magnetic field, right? So therefore here how electric field is oriented. So how electric field is oriented? The electric field is oriented parallelly with respect to what? YZ plane, right? So electric field is uh, parallel, right? Parallel to YZ parallel to YZ plane, right? So electric field is parallel to YZ plane. So this is parallel, right? Electric field is parallel. So even in this direction, or if the electric field is in this direction, or the electric field is in this direction, or the electric field is in this direction, all these are parallel to what? Parallel to the YZ plane. YZ plane is nothing but your screen, right? Mobile screen. So therefore all these are all these, right? So all these are parallel to YZ plane, right? And magnetic field is vertical to what? Vertical to YZ plane, right? Magnetic field is vertical to YZ plane. YZ plane is nothing but your screen, mobile screen. Therefore magnetic field here how I have indicated here with a dot, right? So with a dot in the sense it is perpendicular to your screen, right? So therefore when electric field is parallel to YZ plane, or magnetic field is vertical to YZ plane, then it is termed as then it is termed as vertical or parallel polarization, right? Vertical or parallel polarization, right? So first figure and second figure, vertical parallel polarization, right? Vertical, parallel, polarization. Don't get confused here, right? So generally vertical in the sense perpendicular, right? Vertical in the sense perpendicular, and we use like that, right? Horizontal means parallel. Horizontal means parallel, but here you don't get confused here, right? So here perpendicular in the sense 90 degrees, right? Perpendicular in the sense 90 degrees, right? And parallel in the sense it may be any, right? So parallel to the boundary, right? It may be um, in this direction, or it may be in this direction, or it may be in this direction. So this is parallel, right? So this is parallel. Horizontal in the sense this one, this is horizontal, right? So this is horizontal, right? Horizontal to the boundary. So this is the boundary. If this is the boundary, this is horizontal, horizontal to the boundary, right? So this is how we can define, right? So therefore, from figure one, right? So you just remember how the electric and magnetic fields are indicated, right? So if electric and magnetic fields are indicated like this, as shown in figure one, right? So let us say this is figure A, right? If electric and magnetic fields are indicated as shown in figure A, it is called as horizontal or perpendicular polarization. If electric and magnetic fields are indicated as shown in figure B, right? As shown in figure B, it is called as vertical or parallel polarization, right? So you just remember like that boldly, otherwise you will get confusion, right? So figure A, whenever the electric and magnetic fields are indicated as in figure A, it is called as horizontal or perpendicular polarization. And whereas if electric and magnetic fields are indicated as shown in figure B, it is called as horizontal or parallel polarization. Sorry, vertical or parallel polarization, right? So these are the two types of polarizations, right? So now we will, this is all the introduction, right? So now we will go into the reflection of plane wave oblique incidence, right? And earlier for normal incidence, so this is the normal incidence. Finally, what is the output of this? The output of the reflection coefficient and the transmission coefficient. So both expressions we have derived expressions for the reflection of normal incidence. And similarly, right? So even this in this topic also, reflection of plane wave oblique incidence, we will derive the expressions for reflection coefficient and transmission coefficient, right? We will derive the expression for reflection coefficient and transmission coefficient. Reflection coefficient. So what is the expression for reflection coefficient, and what is the expression for transmission coefficient, right? But here we will consider two cases. Case one, horizontal polarization, and case two, vertical polarization, right? So in horizontal polarization, we will derive expression for both the reflection coefficient and transmission coefficient, and similarly for vertical polarization also we will derive the expression for reflection coefficient and transmission coefficient. That is what we are going to discuss in this, right? And that we will see in the next class. And mm, okay, so let us close our session at this point, and we will discuss in the next class, right? Just a minute, let me stop live streaming.